Welcome everyone. So we are all here together again. Today is Saturday, not Sunday, because tomorrow I will not be able to stream, but we're all here together at Microsoft Office, and we're gonna solve some LeetCode, preparing to interview. Then we're gonna switch to system design as always. First of all, I actually want to review some of the existing system designs on YouTube, because previous time we started and actually the solutions that they were proposing, they were not that good, to be honest, and we noticed quite a lot of not working things. So yeah, let's wait maybe a couple of seconds for people to gather and we're gonna start. Okay, so let's start. Today we're gonna review actually very interesting question, but before that I want to sort out the question problem we were sorting out previously during the previous stream. It's the problem called delete node in BST. So I actually want to do one thing. I hope you all remember what is the solution for this guy. It was quite tricky for me initially, so yeah. I want to refer to one particular lecture from the MIT and about binary search tree, and the thing that I quite didn't understand why they were pointing it like that. So for sure in regular computer science classes they're gonna overview what is the binary search tree, what are the properties, complexities, and stuff like that, and also the possible operations. So the thing is, what I wasn't happy about previous time about this thing. So these are binary trees, part 1, and yeah, so basically about deleting the node from binary tree or binary search tree in our case. What is interesting about it, the actual solution, I don't know whether it's visible here, but whatever. So the solution that we designed, actually, it works as the following. We have basically 3 cases. One case, if the node is the leaf, this is the simple case. Then we just set the pointer from the parent to null. So we just drop the leaf node. Second case, when our node that we want to delete, it has only one child. Then in this case, what we are doing, okay, let me actually draw it. So we have 3 cases over here. So first case is when node to be deleted. Yeah, this is how I'm gonna draw it. So the red one is the node that is going to be deleted when it's yeah, like that. So when this node is actually the node we want to delete, what we do, we just remove this pointer, and this is no matter what is going here, right? It can be some big tree. No matter what is going on here, it's done. Second thing, when our parent, when our node that should be deleted has actually one children, and this is its parent. In this case, if we just detach this link from the parent to the child, we will lose all this subtree that our node that wants to be deleted had before. So instead of just deleting this pointer, we point it to the child of the deleted node. This is second base case, which is kind of trivial to implement. And the third case, which is the most tricky one, is the case when our tree has 2 children. So in this case, if we detach this link from the tree, yeah, this node will stop existing this whole tree, but we are losing these 2 subtrees. But we cannot just relink one of the child from the parent, because we will lose another one. So what is the solution in this case? Well, as previously we did, we either find a predecessor or a successor of the in-order traversal. So basically, we either find the maximum value on the left subtree or the minimum value on the right subtree. So maximum value would be here. We're exchanging the marks or labels between the node to be deleted and this guy. So like that. And then we have a kind of second or first case for this successor, because we need to delete it now. And in this case, it can be either second case or first case. In this case, it's first case, so we just remove this link as well. And this is how the deletion is done. So basically, again, recalling, bro got tourist accent. Of course, I got tourist accent. Come on, I'm in Prague for last 3 years. I'm working with international team. So yeah, my accent right now should be something like mixture of Serbian, Bulgarian, Croatian, Turkish, and like other nationalities accent of English. That's kind of expected. But yeah. Okay, whatever. An interesting part here, what actually is shown for the deletion in this MIT section. So let's listen to this.
If I have a left child, the predecessor would actually be higher in the tree, and I don't want to go higher. Recursion is just by moving.
Let's check the deletion.
Which is.
Oh, come on, YouTube. You can do it.
Okay, now here's a trickier one. Suppose I wanted to delete the root of the tree. This is kind of the hardest case. But in general, it'd be somewhere in between leaf and root. So if I want to delete A, if I just erased it, then suddenly there are these pointers to nowhere, and I disconnect the tree into 2 parts. I don't want to do that. I need to keep my tree connected. So I'm going to play this trick, which is, I forget if I use successor or predecessor. Predecessor.
Okay. So left subtree.
So I'm going to look at A. We already have defined successor and thereby predecessor. So I'm going to look at the predecessor of A, which is E. You can check that here. The one before A is E. This is in the left subtree. Find me the rightmost item. Keep going right until I can't. That's E. So now these guys are adjacent in the order, and I'm about to remove A from the order. So I can momentarily cheat and swap their labels. I'm going to erase A and E here and put E after A.
Exactly.
Why? Because it moves A down in the tree. And if I get to the leaf, I'm done. So I'm not quite done because this is not a leaf. So again, I look at A's predecessor. It's now G. Predecessor, we hope.
Actually, in this case, in this particular case, we are supposed to be kind of almost done, because now the trivial part that is left, we got this second case when the node that we want to delete has only one child. In this case, if this is the node we want to delete, if it has left child, we just remove this pointer and move it here. If it has right child, we remove this pointer and put it to any single child, whatever. So in this case, we should remove A right now, right? So B should be pointing to this, whatever it is not. I don't know what is it.
Is always in the farther down in the tree. And then I swap A with G.
Yeah, this is quite an unnecessary action. This is redundant. We don't need to swap anything else. This was my kind of surprise, because first what I did, I solved this question, I looked at the solutions, and this is indeed the solution. And everybody is talking about 3 cases specifically, but here I was a bit
Okay, I have
confusing.
preserved the traversal order except where A falls, just by moving A earlier in the order here. And now A is a leaf, and I can erase it. In reality, it's a little tricky. Sometimes we need to use predecessor, sometimes we need to use successor. Okay, So the cases are, if the node is a leaf, just detach it from the parent.
That's true.
Easy.
That's
sort
true.
of our base case in the recursion.
Exactly, showing you straight away, this is what we are doing. So if this is the node we want to delete, what parent should be pointing to? It should be pointing to nothing. So we basically detach the node. This is quite correct.
Otherwise, there are two cases. So if we're not a leaf, that means we have a left child or a right child or both. Both
Yes.
is going to be the easy case. But in general, I have either there's a left child or there's a right child. In either case, I'm going to be happy, so I don't need a both case. OK, so what do? If I have a left child, that guarantees to me that the node's predecessor is inside that left subtree, which means it's lower in the tree. If I didn't have a left child, the predecessor would actually be higher in the tree, and I don't want to go higher. Okay, so if I have a left child, I know the predecessor is lower, and so I'm going to swap my item, the contents of my node, with my predecessor's item. Predecessor. If we have a right child but no left child, we just do the reverse. We swap down. We're walking down, which means the worst case.
Exactly, and this was my kind of confusion in this case, because actually here we also have three cases, whether the node is the leaf and whether the node has either left child or either right child or any of them, or like both of them, which is kind of a bit more complicated algo in my opinion, because the only case we need to deal with the successor or predecessor is when we have both children. So in case we have only one child, well, we can just relink the parent to the child of the deleted node, and that's it. And only in case we have two, we have to deal with this like BST magic. Anyway, this was the thing I wanted to mention because I forgot to mention them last stream. Now what we're gonna do, we're gonna get to our graphs. So now it's graphs, and this is pretty trivial problem, but we're gonna solve it with 4 different ways, because these 4 ways will be needed in our next streams, because we're gonna solve quite a bunch of problems with graphs, and some of them will require any of these algos. So let's read the problem statement first. Number of provinces. So there are n cities, they are connected. Okay, so this is disjoint set basically. Province is a group of directly or indirectly connected cities and no other cities outside of the group. Exactly. Unfortunately, the matrix here is represented as, the graph is represented through the matrix, which is the least convenient way of representing the graph, right? Because the most convenient for me is adjacency list. This is the best one I'm very happy to work with, but unfortunately here we have matrix, so this is first complication for me in this problem. So what matrix tells us? If there is connection between I city and j city, it will be having the value 1. Otherwise, it will have value 0. And we should return the number of provinces. So if we have all nodes disconnected, every single city is considered to be a single disjoint set, so single province, we return 3. If they are connected, then this is single province. So 1 and 2 is single province, and 3 is another single province. So this is how we're gonna return. The data structure we are looking for is called disjoint set in this case. This is kind of the data structure that helps us to identify the these particular graphs that are separate between each other. So let me show you and draw you an example. So yeah, it can be something like this in our graph. So let's say this guy, this guy and just separate guy which is not connected to us. So this should be province number 1, this should be number 2. And so the definition of the province is actually connected node in which from every possible node in this joint set, we can reach any other node in this joint set. So for example, from this node, I cannot reach any of these nodes. But from any of these nodes, whatever I pick, I can traverse and reach any of other nodes. So this is kind of the thing how we're going to do it. And what is the simplest way to check the reachability is actually to use breadth first search or depth first search. So first one goes as far as possible. First one explores gradually our graph. Second one explores in a deep way, so it goes to the farthest possible, and then it traverses back. It kind of backtracks. So we're gonna implement using DFS, but DFS we're gonna implement both recursive version and iterative version, because one of the follow-ups on the interview is usually whenever you have recursion, interviewer might ask you, okay, so we are out of call stack, how are you going to solve this and change it to iterative solution, right? So the first implementation that we're gonna do through the DFS recursive one, and also I want to change the matrix from matrix way to adjacency list way of the graph representation, and we're gonna do this just to show. This is kind of, I never implemented iterative DFS. Well, yeah, today we're gonna do this because yeah, this is quite usual. Like, happened to me quite sometimes when interviewer were asking you for a problem, you're implementing it recursively, and then the follow-up, okay, change it to iterative. If you don't change, it's kind of minus because yeah, you solve the problem, but it's not the best solution because yeah, recursion quite almost always is worse actually than iterative solution, because it's additional function call which is more heavier, which is heavier for the CPU because it needs to look up the call table, or sorry, this method table or whatever the call function is itself, takes a bit longer in CPU time and stuff like that. For iterative, I will just use BFS. Maybe that's acceptable. Yeah, it's also acceptable, of course, but the difference is actually not that big. You either use stack or queue, and this is the difference between DFS and BFS. Anyway, so first one, how we're going to define the province. So we're going to iterate over all the nodes. In this case, let me draw some more representative examples. So we're going to iterate through each of these nodes. And we have visited set just to track the record of the visited or not visited nodes so far. I'm gonna label them right now. So let's say we start at node 1 or any node in this subset, and we check whether it is visited or not. If it's not visited, well, this node is not explored. It might be a province, so we increment our number with provinces by 1. Initially it is 0, now it's going to be 1. We run DFS or BFS, whatever algo you use, it doesn't matter that much. And DFS or BFS is going to traverse all the nodes and mark all of them as a visited. So we're going to have 1, 2, 3, 4, 5 in our visited set. And our province is still 1 because we're initially on the index 1 still, or index 0, whatever it is. So we're on the city 1. And this way we kind of explore this province. Whenever in our for loop later on, we're gonna check node 2 or node 5, we already know that it is in visited set, so we don't increase the province count, right? At some point, we're gonna get to node 8, and it is not in visited set. We call DFS, it explores to nothing because this is the only single node. We change 1 to 2. There are 2 provinces now. At some point, we're going to get to 7. Exactly same situation happens here. I forgot to add 8. We call DFS or BFS from 7. It explores everything. And this way, we will add to visited nodes this and this guy. Also, add in the province count, and that's it. Any other time, whatever we try to touch, it will be just constant time check that the node is already in visited set. This is going to be kind of the solution in our case. And let's basically implement. We can actually change to BFS later on, just for sake of example. It's not that it's hard to implement or something, especially when we're gonna have iterative DFS, which is kind of, we should just change queue from, a stack to queue data structure, and this is gonna change you from DFS to BFS. So first of all, just for simplicity, I actually gonna implement the adjacency list because this is a convenient way. Later on, we're gonna use this matrix exclusively, but just for the sake of example, I would like to demonstrate like the adjacency list approach, because this is pretty much common way of the graph problems, and usually you're gonna work with adjacency list, not with the matrix, because no one likes matrix in graphs. Let's implement it. First, I'm gonna convert this matrix to the adjacency list representation. So how we're gonna do this? Since let me also show you this example. So let's say we have this specific case, 1 1 0, then 1 1 0, and 0 0 1. So in this case, you know that nodes under index 0 0 is connected to itself, which is kind of makes sense in a way. So the thing is that we kind of omit diagonal here completely, because it does not say anything about this graph, and we don't care about node being connected to itself. Exactly the same thing happens in this example. You see there is no connection between the nodes, but we still have ones on the diagonal of the matrix. So these guys we just skip, and we have this set to 1. So the row is 0 and the column is 1. So 0 1 in this case is going to be connected, since it's one index base, so it's 1 2. And same happens to this guy, which is row 1 and column 0. So you see that they are kind of interchangeable because it's undirected graph. So we're going to traverse the matrix and just catch this relationship through the adjacency list, and this is it. Okay. Sorry, not list. I also like capture. It will be a bit easier later on. So let's first we just iterate every possible value in this matrix to understand whether it should be added to our list or not. So first what we check, if this guy, we should add one more loop. In the constraint it is stated that n equals to, n will be both width and height of our matrix, so we use just same thing here. Okay, and now what we're gonna check actually, if this guy is equals to 0, we know there is no connection between I and j, so we completely just skip. If it does equal to 1, well, what we should set, we should point that this graph has this node. So it's gonna be node, I think, not I, yeah. And we either setting it, sorry, it's not add, it's set. Either set it to I, or to should be array, or should it be, yeah, let's make it array. Yes, and then we're just checking if I is not equal to j, this diagonal case. We just don't do any connection. Oh, sorry, if it's not equal, it is exactly the connection, because we don't care about capturing the relationship that node is connected to itself. It's kind of already known, and we don't care in this problem about this. So we are getting the adjacency list of CTI and push j to this adjacency list. Basically, it should be it. And now let's do a DFS implementation, which should be quite easy. We have visited. It's going to be set. Actually, can be still array in this case, because we know the number of all nodes. They are starting from 1 to n. But I prefer set as a more natural way. Anyway, so that would be it. And let's implement our DFS. So we have city, and pretty much more natural way, but a bit longer way would be for me to check it in the DFS function itself. So if the visited has this city already, we just return. Otherwise, we straight away marking this guy as visited, and then we gonna explore adjacent cities and put it to our and calling basically DFS from it. Yes, and this way we are exploring all the cities from the node C and marking them as visited. Yeah, that's basically it. And now what we're gonna do in this particular case, we're gonna actually traverse the all guys in our graph, so all the nodes, which is actually would be the same as traversing everything from the 1 to n. So we can do this as well, but let's do it in a more natural way so you have an idea, right? So we are traversing city of graph keys. And now what we are doing, if this guy is visited already, visited has city, we don't do anything. And this is our provinces equals 0. Kind of do nothing. In other case, we just add in this. Oh no, we don't even need to add. We just call DFS from this city, and it will ensure everything will be visited. Everything should be okay. And since the node was not visited, it means we just explored new province. So we adding it, and in the end we just return provinces. Okay, and visited should be actually defined here. Good, good. This is not the best algo you should come up with, so we're gonna improve it in a bit. So first let's check it works. Cannot get edge because of initialization. Okay. Yeah, sorry, this is complete bullshit what I wrote. And this should be the... Okay, it works, let's submit. Okay, it passed, but the runtime is not quite good. So first optimization here. Actually, since I told you the function call is almost always more expensive than the iterative one. So instead of this thing here, what we can do, we can remove completely this visited thing here and move it under the for loop. So instead of additional DFS calls, we're gonna just not do anything inside this for loop. So if not visited has adjacent adjacent. So far we call DFS on it and we mark visited straight away. Visited, it's add, right? Yeah. But now before the call to DFS, we should also add it to visited. Visited add city. This should be actually the first optimization here. Which should work actually as well. Yes, the next optimization what we can do, we can change our DFS from recursion to iteration, to iterative solution basically. So how we're gonna do this? Whenever we're iterating over all the cities, instead of this guy, what we're gonna do? We're gonna introduce stack, and stack in JS is basically the array. And what we are doing here, or stack maybe might be introduced here. Stack equals this guy, or sorry, instead of this, we're just putting city into the stack straight away. We're adding it to visited. And then what we are doing while stack length is more than 0, so while we have some nodes, adjacent nodes to process, we exactly do this. So in this case, it's going to be adjacent, or no, it's going to be city, in this case, stack pop. You just remove it from the stack. And then we can basically copy paste this for loop completely here. Yes, like that. So we're getting adjacency from the city C. If it's not visited, we're putting it to visited, and instead of DFS, what we should do, we should put it to our stack. And then, yeah, we don't need, this is how we basically converted recursive one to iterative one. Let's check it works. It does. Let's submit. Cool. Now, what I'm still not happy about here is about converting this matrix to graph. Actually, we don't need this. We don't need this. We can do better. So far, our complexity here is n squared because we traverse whole matrix. And then for every item here in this matrix, this is going to be n. And exploration part gonna be, so we actually in this traversing, we're gonna touch every node pretty much constant number of times. So this is going to be considered pretty fast. So I would say this is n, and overall complexity in our case is gonna be of n squared. And for the space, since we have okay, if it's interconnected, so for this guy, it's gonna be n squared as well, because we're converting the matrix representation of the graph to adjacency list representation, which we're gonna optimize as well, and we're gonna decrease our space complexity to n soon. How are we going to do this? So instead of building the graph and then traversing the nodes in the graph, we can leverage already existing matrix representation of this graph and do it here basically. So how are we going to do this? So how many nodes exactly we have? We have n nodes. So basically we need to traverse every single node. And then from this node, we can call, for every single node, we can check the adjacent, whether this node is connected to any other node. And if yes, then we're gonna do DFS. So how it should work? We have this for loop. This for loop gonna basically traverse through all the cities. And first thing here, let me move this guy a bit upper. Yes, we're going to convert it now to a bit better solution. So first of all, if this guy is visited already, we just continue. If it's not visited, we again increasing provinces. Exactly like that. Now, we're increasing provinces, but okay, not maybe that. Yeah, we're increasing provinces, and we should start our DFS. So where is our stack? Yeah, this should be our stack. Our city in this case is I. And now, yes. Yep. So, yeah. Now we're gonna just move completely this thing here. So our iterative DFS comes into this loop. Yeah, we are popping the value here, and since we don't have our graph representation here, what we should check, actually we have our matrix, and if our matrix with index I, our current city, to any other index j which we're gonna iterate over equals to 1, then we kinda gonna consider this as a connection. So instead of this for loop, we are changing it to this adjacency equals 0, less than n, and plus plus. Now, if we have, it's not matrix, how it's called, is connected, I guess, I and adjacency equals 0, we basically continue. We don't do anything because there is no connection between these two. Now, if there is connection between these two, what we should also check that this connection is not something that we already visited, first of all, so we will not add this guy here. So instead of this, we can or visited has adjacency already, or our other case that we should consider is this diagonal, because connection between node and itself we don't want to consider. So if node I equals to adjacency equals to adjacency, then we basically continue. Otherwise, in all other cases, we're adding it to visited and we're adding it to for exploration for later. I think this kinda should be it. Yeah, let me actually check whether it works or no. Seems like that. We don't need this graph, by the way. Oh no, it doesn't work. Okay, so what happened actually? What happened? If visited has... Okay, then we add provinces. To return provinces, we add stack. Okay. It is just a simple question of number of connected components. Why a stack is needed? Yeah, it's simple trivial problem. A stack is needed for graph exploration, which is basically iterative DFS. Or you can use, I don't know, Q for BFS, doesn't matter. Okay, so... Yeah, good. Okay. Is connected. Okay, otherwise we add it. Okay, interesting why it does not work. It should actually work. It should actually work. Okay, let me check actually. I see. I guess this was the problem. Oh no. What the hell? Yes, sorry. Can't you use disjoint set unit? Exactly. This is what we're gonna do later. But I first want to check why this thing doesn't work. It actually should work. And why don't we have? We should have nice wipe still. Yes, I think now it's much better. Yeah, still tiny optimization, but it's not the error for sure. It still has. This is actually very interesting. I don't understand why it doesn't work. It should work. So let me build a bit of debugging will happen right now. Come here. Have fun while solving. Yeah, thank you, thank you. I am having fun big time. I don't understand, like this is literally, it should work. I don't understand how come it doesn't. I literally doesn't understand this. Okay, let's go through it once more. So we're iterating over every single city. Let's first of all rename this guy. I'm very surprised it doesn't work, to be honest. Yeah, maybe this one will help us. So first renaming is if visited has city, we continue if it doesn't have. So we push it to stack. We should actually call visited at for this city. Oh my god, I found a problem. We should work with the city we just popped from the stack instead of the city. So I got the problem, actually don't need the renaming. So we popped this city from the stack, but actually we were working with this one in the for loop, not the one that is on the stack. So this was the problem. Oh my god, this is so stupid. Anyway, yes, exactly. Now it should work. It's pretty much optimized solution for now, because from the time complexity standpoint, what it should be, we are traversing whole matrix, which is n times n, which is n to the power of 2. So time complexity remains the same. And for this stack one, we actually, once we're going to explore it, what we can state that we're going to touch every single I and j pair only once, because yeah, stack can go further, it can explore since it's DFS, but next time when the node will be called during this for loop, it will be kind of okay. So this one gives us n, and this while true potentially gives us n as well. So actually, how is even easier to analyze it is to count how many times we're going to visit every single city, and this is going to be 1. Or not the visit, we actually going to process the every single city only once, so it's n squared. Well done, going through solution always works like charm. yeah. This is one of the problems actually. You see, I pasted it to Visual Studio Code, and it straight away noticed that my variable c from stack, it just didn't. It is not used. In a real interview, actually, it will not help me, because if it's whiteboarding or something like that, I'm fucked. Well, so time complexity is n squared, since we are processing every single city once. For the space complexity, our stack can be maximum n, so it's O n. O n, exactly. So, yeah, and sorry, visited also should be O n in the end. It will be. That's it, but there is one more solution, as one guy in the chat proposed. So the question was, can't you use DSU? So what is DSU? DSU is, as far as I remember, this joint set union or something like this. Is it? Yes, disjoint set. Disjoint set, just disjoint set union. Yeah, exactly. What is this algorithm about, and what is this data structure about? So this is pretty interesting one, and why I mention it, because during the next of our problems, it will not be enough just to use DFS or BFS for the next of our graph problems. So what is this disjoint set union about? Let me actually explain it. We're going to drop everything here, because we're going to implement it through this algorithm. This is going to be our third solution, which is pretty much will be the last one for today for the LeetCode. So what about this disjoint set union? let me draw you again the example. So let's say we have 3 provinces in this particular case. So we have some number of connected graphs. I don't know. This is our province 1. This is our province 2. And this is province 3. So how this joint set helps us? So this is the data structure which is applied to the graph where not all the nodes are connected, or sorry, otherwise it applies to the graph that doesn't have all the nodes connected between each other. So not every single node can be reached from any single other node in this graph. This is exactly our case, because let's say if I'm picking this node, I cannot from this node somehow reach this guy because there is no connection. That's why we have this joint set, and this joint union set can answer us basically one question. So after you build the disjoint set fully from the graph, you can pick any node or any 2 nodes. Like let's, let me change the color. You can pick, for example, this node and that node. And what this joint union set can tell you whether this node can be reached from each other or not. So if I'm picking these 2 nodes, the answer will be false. And this answer will be pretty quick. It will be constant time answer. Yes, and also it can pretty much answer the question how many these disjoint sets are presented in the graph. And pretty much that's it. Actually, the implementation is quite interesting. You can naturally come up with this solution, to be honest. But yeah, how are we going to implement it? So actually what I want to achieve in the end, that I'm picking this node, or picking this node, or picking this node, and I know that like I can compare the answers from these nodes, and I can in pretty much constant time decide whether these 2 nodes can be reached between each other or not, or these 2 nodes. How can I do it? Well, I have to somehow present this disjoint set as using the data structure here. And how the disjoint set works, that disjoint set it promotes one of the nodes to be representative of this disjoint set. So let's say I start to build my disjoint set using this guy. It means that this guy will be representative of all other nodes that are reachable from this node. So I'm doing DFS or whatever. I'm exploring the graph, and whenever I know that from this node I have this connection, and that connection, I just keep track of, I'm using array to keep track that these 3 nodes, they have exactly same representative. So I'm putting that representative of node 2 is going to be node 1, node 3 is going to be node 1, and node 4 is going to be node 1. Then I keep going, and then I go to node 5. Let's say, from node 4 to node 5. I see that the representative of node 4 is node 1. So I'm setting the representative for node 5 also node 1. So this way, while I traverse all the nodes here that are reachable, I can say in constant time whether this node, what is the representative of this node. And all of these nodes should return me this guy, the node 1. So whenever I'm reaching to any of these nodes, I'm getting node 1. Same thing happens to this guy. Let's say I'm starting with this node. So representative for node 7 should be node 8. And same happens to this disjoint set. Representative of node 8 is node 9 is node 9 itself. So now how can I check, for example, that node 2, whether node 5 and node 7 are reachable between each other? I'm returning their representatives, which is node 8 and node 1, and I know that node 8 and node 1 are not equal between each other. So I know these are 2 different disjoint sets. Or another example, if I'm taking node 3 and node 4. both of them will have same representative one, so they are in the same disjoint set. It is maintained through the array called parent. So parent for specific node should return this representative. So representative also can be called as a parent in our case. So you know, whenever we are calling parent for some node, we're returning its representative in its disjoint set. Note also that every representative is parent of itself. So representative is representative of itself. So whenever we try to check what is the representative for node 9, for node 1, or for node 8, we know this will be respectively node 9, node 1, and node 8. Now let's pretty much build this algo, and what we're going to do in the end as this algo, we're going to just check and count all the nodes that are representative of themselves, which means they are the representative of their own disjoint sets. How are we going to implement it? So first of all, let's define our representative or parent array. We're going to do a bunch of optimizations later on to improve our complexity, but overall idea should be the following. So first of all, we need to write a function that's going to find the representative. In our case, yeah, how it's going to work? It's pretty simple. Get parent. So for every single node, parent should be what? Should be the node called parent. Yeah, but wait. First of all, parent is not exactly representative, because if we're traversing from node 1 to node 4, parent for node 4 gonna be node 1, but parent for node 5 gonna be node 4. In the end, through the optimizations, we will set it that parent of node 5 is node 1 to just eliminate the number of hops between the nodes. But initially, parent of 5 gonna be 4. So how we're gonna do this? That we're returning representative node, but by following the chain of parents up until we know that this is the representative node, because parent of 1 gonna be 1 as well. So this is not array. This is going to be length. It's gonna be n, and also furthermore we are setting this guy. Initially we are setting this parent array exactly to this one. So every node is representative of itself. Parent I equals I. Now how are we gonna get the parent? Well, if parent of the node is not node itself, this guy, so we know that it is not representative. It means that representative is somewhere upstage, like up to the tree. So what we are doing, actually let me implement this way. Let parent about p be this guy. Yeah, and while p is not equal to node, p, what is the indentation? So p equals get parent recursive call get parent to of parent of node of p, sorry, p. Yes, exactly. And then in the end we return this p. This is how we're going to get the parent. Now, a few words about how to build this tree. Well, we try and we start to exploring the tree, so moving from one node to another. And how we are doing it, that we are iterating over every single node. And if we see that two nodes are connected, we basically checking what is the parent of every single node, because, yeah, let me actually show you a bit better example. So I'm gonna remove all of this. So initially we are not connected at all. What the hell? Why this doesn't work? Okay, I'll draw another one. Good, I can draw. So initially, we have, let's say, this number of nodes, and they are kind of not connected. There is no parent relationship. We only know that parent of the node is the node itself. Now, let's say we explore that this is the connection between nodes. So I will be drawing the disjoint sets with the blue colors. So let's say we're exploring node 1, node 2, node 3, node 4, node 5, and node 6. We're exploring the connection between node 1 and node 2. Man, I wish I could actually start LeetCode and just procrastinating. Well, I'm usually also procrastinating, but the thing is that, yeah, it sounds something I want to get my skill back, so yeah, I want to, yeah. Especially when you, for example, in some cases when you are going to have some interviews, it's very good motivation to not procrastinate. So let's say we have this connection from node 1 to node 2. These are the separate unions. So far, what we are doing, we are uniting, or yeah, we are calling union or these two nodes. And how we do the union, we just make parent of one node to be another node. So parent relationship, let's say, will be this one. Now we're, let's say, exploring node 1 and node 3. Again, we know that parent of node, or no, actually the better example would be node 2 to node 3, this guy. Now we see that they are not in the same union. How we can check it? By this parent function. So since it's the case, we again calling union of these two separate union sets. And let's say we choose parent of 3 to be 1. Oh, sorry, to be 2. Now we have this union set with 3 nodes. Now we're exploring node 3 to node 4. Again, these are two separate sets, and we call union function, and we setting parent of node 4 to any of these nodes. In this case, it should be actually 3. And now, if we want to check whether this, like let's say node 2 and node 4 are reachable and they are in the same disjoint set, what we can do, we just finding the parent of both of them. So parent of 4 is 3, parent of 3 is 2, parent of 2 is 1, parent of 1 is 1, so we found the parent 1. And same parent function we call for node 2. Parent of node 2 is 1, 1 equals to 1, yes, so they are in the same disjoint set. Exactly same thing happening here. So how we are doing union function, we have node 1 and we have node 2. And how we are doing it, oh, sorry, I need to move this a bit to the left. Parent 1 is going to be parent of node 1, or representative rather in this case. This is going to be parent of node 2. And what we are doing, we're just calling parent of any of them to be the other one. This is it. This is basically as simple as that. Now, what is the algo in our case? We're again gonna traverse every city from 0 to n. If not if so far. And to check the connection for every single city, we should check every possible. Yeah, so for our matrix, it should be let C2 equals 0, C2 less than n, C2 plus plus. So if C equals C2, we just skip. Or if C, is connected C and C2 equals to 0. I'll I'll try, so it's good to see someone solving questions live. Maybe I should get Otto my bet as well. Thanks for the motivation, bro. Yeah, you're welcome, you're welcome. Yeah, actually you should have good reason to do this because actually for the past 3 years I pretty much almost never did any LeetCode questions because it requires a lot of time, effort, and usually I was busy with other stuff. So yeah, I'm not doing it pretty regularly. However, you should do it. It's much easier to preserve your skill doing it daily, like one question, stuff like that, than before the interview to spend like 3-4 months, very hard preparations and stuff like that. But it depends, right? So now, if this guy is 1 and if it's not itself, we know that there is connection between C and C2. So what we are doing, we are calling union between C and C2, which is gonna do this relation, right? And once we are done, we are doing it for every possible connection. Once we are done, what we are going to do, we are going to traverse our parent, so C0, C less than N, C++. And actually our parent function returns us the representative. So what we're going to do is actually check if the node, if the parent of the node is the node itself. If it is the case, this is the representative of this joint set. This is a representative of the province. So we increasing our province. How it looks like, if get parent of the C equals to C, then we increase provinces. In the end, we just return it. Actually, the complexity of this disjoint set implementation is very bad because we don't apply 2 main improvements to the disjoint set implementation, which we're going to do in a bit as well. It passed, as you can see, and let's check all test cases. Yeah, it passed, but the runtime is 9%, very bad. We're going to do it much better. There's a question in the chat. Is it for 1 question a day? It works. I have my placements in like 2-3 months. Well, I would say, personally, since I was preparing for AWS interview, failed it, and then for Microsoft interview and passed it, I would say that actually you should start preparation for LeetCode problems at least 2 months before. And if you have only 2 months and you will have interview with some big tech company, so you actually want to be prepared well. You want to check all the possible patterns of the LeetCode questions, get used to regular problems, to have this pattern recognition for the problem, to not waste the time and to not do stupid things during the interview. So yeah, 2 months of 3-4 hours per day. I think this is the minimum boundary for a big tech company interview if you haven't done LeetCode like 2 years already or more, or a year and more. Because yeah, skill of these LeetCode problems, it is the skill that you gonna lose if you don't do it regularly, and this is kinda expected. So yeah, and if you already kinda spent 2-3 months and you kinda up to date, your form is in very good shape right now. Yeah, I think it's just good to solve one daily challenge, and that's it. So how are we gonna improve this guy? So first problem in our case is the get parent, because let me also throw you an example. It can be a situation like the following. Let's say we have this graph, which is actually like linked list. Let's say we are starting our representative with this guy. We saw the connection between this node 1, 2, 3, 4. We are setting parent of node 2 to be 1. Then we exploring this guy. We set parent of 3 to be node 2, and fourth node, the parent of the fourth node should be 3. Now, how do you think much time we need to check to get the representative of this disjoint set by checking node 4. So we're gonna go from 4 to 3, from 3 to 2, from 2 to 1, and with these 3 hops, we get to our representative. Is it efficient? Actually, it's not. It's not efficient completely. Are you preparing for interviews at the moment, or are you doing this for the love of the game? No, I'm not preparing to the interviews at the moment. I just want to get back my skill and to be up to date, because if you check the LinkedIn and like official Microsoft announcements, they announced layoffs. And you know, when your company is announcing layoffs, you want to be kind of prepared, right? So I'm just getting back to my shape, you know, just to have backdoor plan. Because you never know, like these numbers, they just go and you can be just laid off due to not even performance, because my performance is kind of okay, I guess, from what my manager says to me. But just due to your project is not needed and we want to save money, you know. So you want to be up to date. So in this case, is the getting the representative of this disjoint set effective? No, because it takes you O of n to get the representative in the worst case. And the more nodes you have in your disjoint set, if these nodes are connected like that, and let's say I'm asking representative of node 6, I should traverse all the way down to the start. So what is the first optimization? The first optimization lies under the parent array optimization. So whenever we are trying to find the parent for node 6, we not only recursively calling the same function for the next node, for the parent, but we also replacing the parent of node 6 with the result of this function. So what do I mean by that? Let me draw you an example right here. So parent of node 1 is 1, parent of node 2 is 1, parent of node 3 is 2, parent of node 4 is 3, parent of node 5 is 4, parent of node 6 is 5. Let's say I'm calling parent of node 3. I know that parent of node 3 is not 3 itself, so I'm calling recursively the function getParent, right? Because I know that this guy gonna be 1 in the end, not 3. Oh, sorry, not this one, sorry. This is our function. So basically, yes. I'm getting the getParent, and it recursively will return me 1. So P is gonna be 1, and I return 1. But I recursively calling node 2 and node 1. By doing that, why not to do the following? So instead of, like every time we call this function for node 3, we are interested in node 1. We don't care about everything that was in the middle. So that's why first optimization is to rewrite parent to the representative straight away. So once we traverse this guy, we know that parent of node is not node itself, not like this case. So what we are doing, we are rewriting parent of node 3 to be 1. First optimization. So next time we're gonna get the representative of this joint set by node 3. In one hop, we're gonna get this parent straight away. How we're gonna do it? Exactly this way. By just overriding it. So next time we are calling getParent on node 3. We know it's not the case. Yeah, and we're calling it like that. So we are jumping to the node 1, and node 1 will return us 1 itself. We're just skipping node 2. Same thing will happen to all other nodes. So let's say we are calling this function for node 6. And node 6 will return us node 5. Node 5 would go to 4 and stuff like that. So we are recursively gonna change it to this one. Oh, sorry. So eventually, after some time, when we're gonna call our function again and again, what we will end up that we're gonna get our representative of this joint set in a constant time. So instead of our, no, I cannot write here. So instead of our 3 like this, It can be pretty deep. After some time, after we call all of the representatives of this disjoint set, the tree gonna be more balanced in a way that we're just gonna do it in a constant time. So this is first optimization, which reduces the complexity time. There is big proof under this thing, but overall, in general, this optimization will decrease runtime from OON to constant. This is first optimization. Next optimization is this guy. So this is a bit tricky one, and let me draw you example as well. So let's say we have two disjoint sets. Let's not talk about this optimization. Let's say we just don't have it. So we have this disjoint set, and we have this disjoint set, exactly. Let's say I want to union them. So what do I mean by that? That I'm exploring these two nodes, and I want to somehow to connect them, right? So yeah, one way to connect them is actually to join the, let's say this guy is 2 and this guy is 1, to join the node 2 to be child of node 1, or vice versa, node 1 to be child of node 3, or node 2, sorry. So which one to choose in this case? Which one to choose? The answer to this question should be the least one. So what do I mean by that? Let's say we have some very long relationship of the tree, right? Oh, sorry, not even this one. Let's say I'm working. Yeah, so this is the node I'm exploring right now, and this is the node that I'm exploring right now. So I'm pretty sure that this is the representatives, right? And the length of this tree is 3, and length of this tree is 4. So for me, it's better to make parent in the way that not that this tree becomes a child of this tree. Why? Because if I just join them, it means that this guy will become something like that. And the length of this tree would be something like that. It will be still 4 nodes. What if we do differently? What if we make this guy as a child of this guy? What will happen in this case? That the length of this disjoint set was 4 before, but now it becomes 5. Because 1, 2, 3, 4, 5. So what is the optimization lies behind when we have two disjoint sets and one of them is has bigger height than another one? We should join another one to this biggest one, because this way the height will not increase. So how it looks like when we got the two parents, we introducing the new array called rank. Exactly same thing. This is kind of something like the length of your join set. Oh, sorry, disjoint set. This is the length of your disjoint set. And how it works that initially this guy is 1. Because initially all your nodes are the parents to themselves, which means they have only length of 1. But once you're going to do union, what is tricky about it is if rank of parent 1 less than rank of parent 2, which means parent 1 or set, disjoint set 1, has less items than parent 2, we are joining parent 1 to parent 2. What I mean by that, that parent 1 becomes a child of parent 2. Same applies vice versa. over here, yes. If it's completely opposite, then parent 2 becomes a child of parent 1. Else, if they're exactly same lengths, we can choose whatever else and just increase their rank. So let's say I'm doing exactly the same thing. But now I know that parent 1 has height plus 1. So it means that rank parent 1 gonna be plus plus. Yeah, I think this is the optimization. This one we ensure that we kind of try to keep as short path to our parents as possible as well. So with these two optimizations, it actually becomes, the time complexity becomes from n cubic to n squared. Yeah, now, yeah. Should be it. So this is like this disjoint set or union find otherwise data structure is pretty useful for disjoint graphs or forests. I think they are another name how they are called is forest. Yeah, so maybe some another optimization. So if parent 1 equals parent 2, we don't do anything. This is also one thing. And now, yeah, actually one more observation that we, in the matrix representation, we can start with c plus 1. This is first observation. And also another thing that we should not traverse and like for all the provinces and check parents, which is still O(n). Instead, we can kind of assume that number of provinces equals to n. And whenever get parent, is it get parent? Yes. And whenever we have different parents, only whenever I have different parents, it means that we're gonna join them and it will make number of provinces 1 less. Because initially all the nodes are separate provinces. Something like that. Yeah, so I think that should be it. Let me also try to run, and now the complexity should be even better. Like, it's not complexity didn't change in a nutshell here at all, but through the optimizations we are doing less cycles kinda. So that would be it. Yes, these are 3 solutions, pretty much same complexity, but what was important during this stream for me is to show this algo, because union find algorithm will be used in the next problems as well. Now let's get back to our URL shortener thing. So first of all, I think we might try to implement it completely. So let me find open folder. Let me find all the stuff I need. Good. So last time I think we set up everything in the Docker. What I mean by everything, let me also recall you what we were doing. Come on, please. Thank you. Let me recall you what we were doing. So our solution is the following. So URL shortener, it was proven that one of the best approaches is to have some kind of unique number generator, which is proven to generate unique numbers. And from these unique numbers, we're going to do just base 62 conversion, which converts the unique number to number of characters in base 62. Why not base 64? Because there are 2 more characters that are not safe to be added to URL. Otherwise, URL can be broken. Well, and yeah, what is the overall system design? that this is the right flow, so we resolve in DNS going to our load balancer, blah, 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 then URL shortener gets the number from which it generates this short piece of URL, and it stores it into the DB and into the cache. Actually, for our MVP purposes, we can use only cache and that's it. Then on the read flow, we're gonna do as well load balancer, blah, 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 and then go to cache and just return redirect 301. This is kind of the scene. And last time what we did, as far as I remember, last time what we did, that we connected both of them, and we were able to get the unique ID, which is pretty cool, because now from this unique ID, what we should do, it's pretty easy. Unique client, and now we're gonna convert this number to base62 sequence and write it to the Redis. But also, as a parameters, I think here we should also, and this is, the application of the AI gonna be used here. So, first of all, what I want to do, I want to accept parameter. In the URL, doesn't matter what is the fastest. Accept the parameter from the URL that what it will be doing, the parameter that represents target URL, which gonna be URL. So the customer sends us the target URL, which it wants to create short URL to. Okay, they want to do it this way. I quite agree with this. Let's do it same way. What happened? Why you can't? Okay. Okay, let's do it this way. No problem. The old way. So this is the class. All right. We actually don't need to be class. I think it can be. A bit of simplification. I love .NET. It is called. And now this guy can be accepted just through the parameters. One more time, I love .NET. So now from this request, also what we should do, we should add the Redis here, Redis. So let me go to my Docker setup. Do I have the Redis here? No, I don't. However, I have Redis for Snowflake auto increment, right? Yes, I do have it. So Redis, I just need to add the Redis to my kinda DI. Exactly, Redis, where is the Redis? Yeah, connection multiplexer. I think this is what we need. It's before build, so this is the guy. Also, we do need the NuGet package. Anyway, I think easier way to do it is this one. And just give him the connection string, because it's proven it was working right before when we were building scalable auto increment. So in this case, we will just ask GPT to generate and ask what package should we add basically to make it work. This guy we can copy straight away. V8 don't need. Oh, actually, it is over. Oh no, it was not supposed to be like this. It's not here. We should have put it here. Oh my god. Yes, and now you need to add stack exchange, right? Yes. So where are NuGet? Please don't lock that much. Yeah, we are adding NuGet. We should resolve our Redis connection, and what we're gonna do, let me actually add service called, I don't know, URL shortener service. It's gonna actually accept and have two functions. Does it include any? Yeah, it does. So I don't want to use Redis exactly here straight away. So instead, what I will do, I'll pass it to my service. And then, yeah, this is the DB, what I wanted actually. Create short URL is sync. Good, and now for the Redis get database. Please, Copilot, help me. Help me out. Some indentation. Is this guy disposable? No, it's not. So it means maybe we can do this. What is the type? iDatabase. Then it seems like we can do this iDatabase and then do all initialization over here. Exactly. And now, what we should accept here? We should accept here string short URL and string original URL. And what we're gonna do, we're gonna write short URL. Yeah, because our mapping on the read flow is gonna be that we got short URL and we're gonna return original URL. So we're gonna set string set, and our identifier gonna be short URL. So Redis gonna be short URL, and as answer should be original URL. And then exactly same little function for returning this short URL back then. Bro, chill, why so fast? Yeah, I don't know, I like to do things fast. That's, yeah, I totally cannot, you know, whenever somebody is sharing its screen to me, I like doing like this slowly, mouse, then like typing something, look into the keyboard, again typing something, look into the keyboard. I generally cannot stand it, so I would rather do it myself. So now what we should do, get original URL, exactly, we're just getting it and returning it. It can be null, yeah, basically we want to convert it to string. Yeah, thank you. Oh, it will be implicitly converted? Seems like it will be. Now we're gonna add this guy to our DI, which stands for dependency injection. Builder server. I think we want it to be singleton. I guess database object should be thread safe. Let's actually double check it. Yes, in Stack Exchange it's thread safe, which means it can handle concurrent operations under hood, which is good, which is quite good. Yeah, one thing we want to do is to assign this guy here. Good. Now in our request, what we're gonna do? Await. Yeah, we're gonna inject this guy here as well. So we need short URL shortener service. Its name is service, whatever. We are creating short URL right now. So our short URL, yeah, before that we should actually compute this URL. Basically, it can be moved straight away to this service. Maybe later on, like when service grows, we can decouple it to a bit better shape. But right now, maybe let's do the following. So it's going to be short unique number. Yes, request target URL exactly. Cool. And now, again, according to our algo, we should convert unique number to base 62. I'm not gonna do it myself. Convert unique number to base 62 string. I will let ChatGPT to do it. However, it's not that hard to do it. Converting to another base, but yeah, this is kind of the algo. Yes, and we're gonna just have it in our singleton over here, and then the method. It's not the best separation of concerns. We shouldn't have access to raw database like that, but whatever, it's MVP right now, right? Tell me one thing. I'm doing web dev right now, and I can build scalable website with much better front end also, but I want to get it to find company or big fat company. What you will suggest me? Also upload this video later. I missed a lot part of this video. Yeah, video will stay on YouTube, so yeah, please don't forget to subscribe. Also, please guys, don't forget to subscribe to my Telegram. Pasting it into the chat. What is my Telegram actually? I forgot it. Yeah, we are doing LeetCode in system design. Usually, currently, we are doing system design implementation, which gonna be, and later on we're gonna review the existing ones. So this is my Telegram. You can find it, or I think it's other name for it is this one. Yeah, so please subscribe. I'm pasting news and my corpo news updates live from Microsoft as a Microsoft Software Engineer Daily here. Don't forget to subscribe. So this is, yeah, video will be uploaded answering to your question. And answering to another question, you're doing web dev, you can build scalable website, how to get to the FANG. So to get to the FANG, you should do a lot of LeetCode problems because algo interview is one of the quite fundamental in their interviews. And another thing, learn how to do system design of different stuff. Do not implement it like me for fun, because I'm doing it for fun, but just do and know how to implement basic system design problems. Partitioning, replication, all these concepts, you should know all of them, basically. Yes, so short URL gonna be base 62 unique number. Yeah, and that's it, and then we're gonna just resolve it. So for the reading part, I will ask GPT straight away to implement me simple get method that accepts one road parameter. Yeah, we're gonna accept it as a road parameter. This is gonna be our short URL that we're gonna. Oh no, I didn't want. Okay, it implemented it already, right? Oh yeah, this is very bad code. No, like not very bad, but typical optimization here to remove async, because async keyword generates a state machine which slows down your code execution. So never do this. If you have one line await statement, just return task instead of await. But okay, this is optimization. We don't care. What we are interested in here is about read flow. This is our short code. We are getting our original URL. If it's not null, we're returning it, but not okay. No. We want results. Redirect. Is it 301? Well, I need 301. Redirects to specified URL. When and are sets the status code. Permanent redirect. We need to move permanently. Okay, let's do just default one. I don't know. Otherwise, not found. Not found is actually good here. Redirect. Let's actually check it works first. And then we're gonna put all together into the Docker with our Snowflake ID, which is scalable unique ID generation microservice, kinda microservice, still not, I guess. Yes, allow. So which one is X account and which one is Insta account? Actually, Instagram account is this one, Andrejka26 SE, and Telegram is pretty much the same. For X, I don't post much, but the most active I am on this programming space, which is X name. Right now it's Andrejka26 SE as well. This is the Telegram channel, and this is where I'm mostly active currently. Good, so we are checking whether our guy is working or not. Yes, exactly. So, no, this is not the local host we want this guy. Okay, so let's basically check, but it will not work since we don't have Redis currently, so it should throw exception basically, because it cannot connect to database, I guess. All right. Exactly, possible to connect to Redis server. So, I think to check whether this thing works together, what we should do, we should... Why didn't I add a readme here? Whatever. So, how do I compose it? So, our URL shortener has load balancer container, which is Nginx, basic stuff. It has Nginx configuration. Interesting, why it doesn't have actual Nginx configuration. It should have. Like that, and this guy should be removed. This is our Nginx configuration copy, which has two Snowflake API containers, and it's proxied to them, and I think this is it. Right, this is it. So we have this load balancer, we have URL shortener container, which is exactly the code we added, and also what we should add, yeah, it should, since the network is system designed for these two guys and exactly same network for our Snowflake implementation that does have Redis, it should be able to connect. It should be able to connect. So what we're gonna do, we're gonna just set up both of them. So what I'm interested in is Snowflake. Does it have Docker Compose? Yes, Docker Compose up. And in this tab, we're gonna go to URL shortener and also call Docker Compose up. Let's rebuild it, basically. Okay, typing speed, monkey tab. Are you on Discord too? No, I'm not on Discord. Actually, let's check my speed of the typing because I didn't do it for a long time. Speed typing online. This is the checker I'm mostly using. So as far as I remember, I should have 400 characters per minute. So let's just for fun, let's check it. Ah, shit. Okay, it's actually a bit better. So only almost 500 correct entries, which is my speed at the moment. But you know, this is a plain text and pretty convenient words to type. And usually when you're typing with Vim and stuff, you have to do a bunch of different stuff, you know. So yeah, I think my record something like 500K. So, oh, sorry, 500 characters. I don't know. Okay, so now, actually, as far as I remember, I used Postman last time. Postman, to check this guy. No, that impressive. Yeah, thank you. I was kind of nerd about typing. Okay, so we do have something, or not found, what is it? What are our endpoints? So we have post. How it worked last time, I don't really remember. We somehow glued it together, but I don't really remember how. So we have our load balancer, right, and Jinx config. Did I remove anything? Let me check the Git story. Resume updated, haha. Yeah. Maybe we just worked without Nginx last time. What? Do we need Nginx like at all? What was our configuration first of all? Yeah, load balancer, okay, so it goes through the load balancer, okay. Okay, I have to remember, so why shortener short? Not found. I don't think it will work at all, so let me actually check what are the ports. I don't remember, like last time we set it up completely fine. So Nginx 5000, yeah, so this guy goes through the Nginx, and we have Redis, which is externally available. It has external port. Snowflake auto increment is not under external port, second instance as well. And shortener is, yeah, they have internal ports. So basically it should go through the Nginx, which means we should just update this guy. We should just update this guy. Yeah, I recalled. Yeah, so we're gonna do it through the ChatGPT. Where is ChatGPT? Come here. Come to Papa. Update this Nginx conf to the following. When I have shortener pass, direct it to the Docker container with the name. And what is the name in our case? Should be URL shortener 1. Yes, actually with HTTP. Yeah, now that we're gonna update our Nginx, it should actually monkey type. Okay, I will try, but a bit later. First I want to run this scene. Okay, now yeah, okay, now what we're gonna do, where's JSON? And what is our model actually? What is our request? Target URL. Let's do this. Not found, so shortener URL. I see what can be the reason actually. Apply the route, not yeah, apply route parameters when redirecting to the wait, what? Wait a bit, wait. I think it changed due to shit. I think it the volumes. The problem is in the volumes because it's concretely connected. Okay, so I have to do a small break, and we're gonna continue. Sorry, small break 2 minutes. Stay with me, guys. I'll be soon. Sorry, one question I'm answering before I'm going. For a quick one, which programming language should I focus to get into Microsoft? Currently working with C#. C# is one of the best choices, but it's not like it will be better or worse in terms of interview. For the interview, you can code in any language you want, but better to be some OP related. In terms of projects, well, in Prague office, mostly you will get some C# related project, which, for example, the project I'm working on right now. So yeah, mostly we are using C#, that's true. So it will help you later, but for interview, it doesn't matter much. So I'll be in a few minutes. Okay, I'm back. So, yeah, what this scene was about, it was about the volume. Let me try again to put it to whatever GPT had. Shut up. So, yeah, this should be the guy. So, I saved it, right? Let me docker compose up build again. So, was it changed? No. And now, let's try to send a request. Not found. Maybe it does not send the pass parameters into them. Yeah, to this guy. Yeah, thank you. So let's try. Exactly. Let's try to rebuild. This time I think it should work. Exactly, it worked. Maybe some exception was thrown. Maybe not. We can check the logs. Docker ps docker logs. I'm particularly interested in this guy. So what we had failed to determine the HTTPS port for a direct. Blah, blah. Ah, no, it's native logs. So we didn't have any logs basically that much. Let's try to assess this. So, but we don't know the short URL. We should also return the short URL. That was my problem. So, what we are doing here, yeah, we should actually short URL because it will be our key in the Redis that we should look up here, right? So that's why we go here, find usages, short, oh my god, short URL equals this guy, and then we return short URL. Now we're gonna rebuild it once more, hopefully the last time for now, and then load tests. Cool, let's check it. So QWERTY, yes, this is our short URL that we have generated. Now if we go, what is our Swagger basically? URL shortcode get method. So I should put it here. Yeah, this is for later use. And now let's try to resolve it. Not found. Yeah, because it should be URL. Okay, this is another not found. This is something that I wouldn't expect. Okay, so this is something different. Ah, okay, so actually redirect happened. It's okay. It's okay. I can prove it like this. So we went to, yes, our service basically works. So this is the short URL that we went with, and what we got as a redirect, we got this is as a redirect. So it's pretty much working. If I define another one, let's say andreika26.com, yeah, if this one, the URL I want to redirect to, and I go here, it will be redirected to my technical block. Yes, basically that's it. If we write something else, it will be not found, blah, blah, blah. So this is it basically. This is it basically. The proof of concept, kinda. The proof of concept. Now how we gonna check it? Like we can do load balancers, for example, for, yeah, previous time what load tests we were writing for Snowflake. These are the tests, and exactly the same thing we can write Q6 tests JS, but for the URL, what we're gonna use, not this one, this one, right? Yes, so for URL we want to check this guy to check how greatly our redirect is working. So it should be 301 all the times. This is what we expect. And what we're gonna do, yeah, for 1000, let's see how my CPU will be working. So for now, first of all, what I want to track Docker stats. So we have the CPU usage and mem usage per container. We have boundaries. Yes, so memory limit 2 gigabytes RAM limit, and CPUs, vCPUs is 1. So 1 vCPU in this case. And what we should see increase of CPU on all the services. So we, we scaled already Snowflake API for scalable ID generation. So these guys, they should be kind of okay, but URL shortener shouldn't handle 1000 per second. Let's maybe for fun, for first time, leave it for 500 requests per second. Yeah, and this is in URL shortener, load tests, and how to run them. It's case 6. How to run load tests. Is it case 6 the name of the file or not? Let me also check with the GPT. How to run case 6 tests. I have it installed, it's okay, just show me how to run. Case 6 run. Yeah, and now let's check how it goes. So we see CPU increase for URL shortener 20%. It's how many? 300, 400, 500. Now CPU is 7080 for URL shortener. Snowflake auto increment kinda works good. Yeah, everything kinda works okay. Nice. So all of them were failed. What the hell? Why? Oh no, everything was successful. Let me just check that we gonna see same thing in case we change it from this guy to something unexpected. We should see all of them fail basically. We should return 404 instead. Yeah, failed all of them. But I'm wondering why checks didn't pass. Come on. It should pass the check. What the hell? What is the pawn status? Or yeah, let's check this guy for 2 seconds. Checks should pass actually. Why 12 2? Anyway. Sorry, I missed the chat. Sorry for missing the chat, guys. Sorry. So hi Andrei, what's the study plan you follow to study every day? I feel overwhelmed and sometimes I can get time for me to study after or before work. Yeah, work is sacrificing, also personal life is sacrificing. So study plan, I'm doing a lot of LeetCode. So I'm doing this 150 interview questions. Before that I was doing 75 LeetCode questions. So going through these questions and learning stuff, right? Learning how to solve it. Then for system design, it's data intensive applications by Martin Klapman, and checking his articles, checking the different distributed systems protocols like Raft, I don't know, for example. And that's basically it. That's also learning Linux a bit. Which problems you solved today on LeetCode? It was graph problems and binary search tree problems. The recording will be on YouTube, so all's good. You have URL algo? Yes. URL shortener algo? Yes. Algo is simple. You're getting number, 64 bits of unique number, and you will convert this number to base 62, and this is kind of your short part of the URL. Okay, I don't understand a bit why it's... I a bit don't understand why we got not 301 but 200. Sorry. $302. I'm sorry. Yeah, it should be 302. Is it the one what we return? Come on. 302 found. Great, let's check again. I don't understand why it doesn't return. Maybe it performs redirects. Let me ask it why I don't catch 302. Ah, yes, so we should put redirects to 0. Sorry. Yeah, let's try again. Because we should ensure we return correct one, right? Yeah, now it's cool. Now it's what I actually expect. So now let's try maybe 1000 requests, right? For the 5 seconds, no, for the 10 seconds. And check the load, and then we're gonna upscale our solution. So we're gonna have 2 instances of URL shortener instead of 1, and let's see how it works. So these are the stats. I hope you can see it. Yeah, so CPU 150 sometimes for 1000 users. Yeah, 150, 50. Okay, so it means if we scale double, we should not get above 100 of the CPU, right? So what I'm gonna do, I'm gonna define another upstream in the Nginx. I'm gonna call it URL shortener. And for this guy, URL shortener scale 2. So it's gonna create 2 instances of this guy. No, sorry. It will not actually work, so I'm gonna just copy paste it from the... Yes, exactly, okay. So let's just copy paste it as well then. URL shortener 1 and URL shortener 2. Exactly. Same characteristics, same everything, but just 2 instances. Then we go to Nginx and just add this guy here. Yes, and then URL shortener, this is what we're gonna put here. Proxy pass. Good. Our Nginx should be kinda ready. Let's set this guy up. Now you should see 2 instances. Yeah, so we have URL shortener 1, URL shortener 2, 2 Snowflake APIs, which we're gonna check on write test load. So now let's see exactly, yeah, let's run exactly the same scene. Where is our load test? Exactly same scene. 1000 requests per second. This is what we are running right now. So it's 500 already. We see 70% of our CPU on URL shorteners. 80, 90, 70, 50, 40. Yeah, it decreases. So it kind of can handle it, which is good. Now, oh, it's not the one. This is the one we wanted. Yeah, it was 1000 anyway. So now, what I want to do, I want to check also write flow. And for write flow, we are doing post. And I will ask GPT to write it for me as well, because I'm lazy. This is the case 6. This is the C# endpoint. This is the target URL. Request. Please create K6 method to load test it. The target URL should be unique one. Good, 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 good. Yes, this is what I want. Exactly. So this is our and this is right flow. Good. For the URL, we're gonna do exactly same thing. Shortener, please. It's already included here. Okay. And payload, we are doing unique thing, which is pretty cool. Let's first try with the 500 requests. On the right flow, now we should see the load on the Snowflake as well. Snowflake ID, I mean. Cool. Let's start and check the load meanwhile. Since it's right flow, yeah, we should see something on Snowflake as well. Currently 200, 300, for 500. Yes, we see Snowflake on 50% of CPU, and our URL shortener on 50-60 as well. Load balancer on 60%, so it means if we add even more load, most probably we would need to scale load balancer and, you know, balance the load on the DNS part, because, you know, everyone on their system design, everyone just points, okay, we can put load balancer, but load balancer is single point of failure, so you should somehow distribute your load balancers between your clients, or DNS actually can do it and put some round robin between your load balancers. When your IP is resolved from the domain name, it gets kind of random load balancer, and this is how you omit load balancer single point of failure and single point of load, basically. So this is our approach right now. However, we have one load balancer, but no matter what, this is for read flow. We don't go to Snowflake ID generator, we go straight away to cache and resolve it. We didn't include this fallback because for MVP purpose it is not needed. In this case, we are resolving unique ID generator and then just put it to the cache so later we can read. For specific hashing and all these kind of things, replication and hashing, it should be a separate topic of the system design when we will be just implementing a replication or partitioning for some specific storages like Redis, for example, and stuff like that, how to do it on-prem without cloud, how it should work and stuff like that. For now, we just use single one just for purposes, and we see that pretty much 2 instances of computes and 1 instance of load balancer, 1 instance of Redis can handle 500 requests per second easily. So yeah, this is our scale your points, kinda. More than that, I wouldn't go, to be honest. Let's run load test for write once more. I didn't check what was the load on the Redis, but Redis should be fine with 500 per second. Okay, it is increasing. We are waiting for 500. So Redis is 15%. Everything else on 60-50, which is exactly the metrics you kind of want to have. Like 50, yeah, it's good. It's good 50. Great. So we have 0 HTTP failed. So latency on P90, 100 milliseconds, right? It's milliseconds, I guess, which is good. Minimum, average, and maximum. What is the maximum? Half a second. Quite good. So that's it, guys. That's it. I think I kinda demonstrated how it can be scaled. However, we didn't mention the scaling of the storages, but it can be done through the easy mod operation or something better than consistent hashing. And as a hashing key, we're gonna use this short URL. As easy as that. I think we are done. Unfortunately, I don't think we have time for reviewing other solutions for system design. How do they implement it? How did they implement the URL shortener? But we're gonna do it next time. At least for now, I think I can safely say that we finished the URL shortener system design completely. I'm pushing everything to my repo. So in case you are interested, what you can do, you can go to this GitHub. I will show you right now to my GitHub pretty much. Yes, I will show you right now. And this is where it is pushed. So you can go to URL shortener and check the code basically. Good, good. I think we are done for now. We are done for now. We have, oh, it's interesting. We have only, I don't know why my metrics on the Twitch are so bad. I don't know. My YouTube performs 300 times better than Twitch. Like usually on YouTube I have 10 on like 8 to 10 average, and on Twitch I have like 3-4%. So I don't know. Anyway, thank you for being with me. Recording is preserved. This would be it. And yeah, see you next time, people. See you next time. Bye bye.